Welcome to this episode, and this is the fifth episode of Physics for SS2. And this particular episode, we are going to be dealing with a topic known as simple harmonic motion. So, I implore you to watch to the end of this video to gain as much as possible. Now, look at these three sets of diagrams. We have three different motions. First, we have the motion of a pendulum from side to side. As you can see, this pendulum is swinging and it is moving from left to right. It's continuing that motion. Secondly, you can see the motion of a mass suspended from a spring. When you have a light mass suspended from a spring, and then when you put that mass in oscillation, vertical oscillation, you notice that the mass goes up and comes down again, and it keeps doing that till the motion fades off. And finally, we can see the motion of a loaded test tube in a liquid. So in the previous episode, I talked about the fact that when you immerse a test tube in a liquid and you measure its height, you can also use that height to estimate the relative density in terms of other liquids. Now in this case, when you in that same test tube, when you load it and you set it into vertical oscillation, it will keep going up and down in liquids for some time till the motion becomes damped out. Now what is common with these three motions is that it is a regular and repeated motion. So each of these is termed simple harmonic motion because they are simple motion of objects that are repeated and regular. Now if we were to formally describe simple harmonic motion, it will be called the periodic motion of a body or particle along a straight line such that the acceleration of the body is directed towards a fixed point and is also proportional to its displacement from that point. So these are three properties and three keywords. The first is that it is periodic. The second is that the acceleration is directed towards its center, and the third is that the acceleration is proportional to its displacement from that center. If we know these three properties of any motion, we can be able to describe the nature and properties of that simple harmonic motion. Most of the time, we'll make use of a reference circle for studying simple harmonic motion of objects. So as you can consider the motion of a particle P moving around a reference circle with centers C and diameters BD and YZ. So as you can see in this demonstration, you can see this circle and you can see a particle P with this ball moving around it held onto it by a string PC. Now basically, let the particle P move with a uniform speed V around the circle of radius CZ equals to C1 equals to A. Now the angular velocity of the radial vector equal to the speed of the particle by the equation v equals to the product of angular velocity and amplitude. Now if we drop a perpendicular from P to the diameter yz to meet yz at Q, Q is called the projection of P upon the diameter. So as P moves around the circle, Q moves to and fro along yz. That is obvious, being momentarily at rest at y and z and moving with maximum speed as it passes through C, the center of the path, yz. Thus, the motion of Q along the diameter yz is simple harmonic motion, while the particle P moves with constant p speed around a circle. So x equals a cos theta. That is the projection of P on the horizontal diameter, where x is the horizontal distance of the P from the center of the circle, and so on and so forth. As you can see in this diagram, you can see that the motion of any simple harmonic object can be safely represented by the motion of an object with constant speed around a reference circle. As a result of the use of our reference circle, we can also represent simple harmonic motion as motion in a straight line. So in this case, you have to represent the center of the motion or the central position, which is also known as the equilibrium position. And then you also need to represent the position of maximum displacement from the center on either side, which is in this diagram we have them as y and z as the position of maximum displacement, and the maximum displacement is also known as the amplitude of the motion, which is um, uh, the the movement of the object away from the center position C. So when it is greatest, it's called maximum displacement or amplitude. Another property of objects moving with simple harmonic motion is their frequency and period. Now, first, the frequency is the number of complete revolutions per second made by a vibrating body. Now, since the time for one complete revolution is equals to T over n, and that is the period. So the number of revolutions per unit time will be equals to what? N over t. That is the frequency. So you can say that the frequency is the inverse of the period, or vice versa. The period is also the inverse of the frequency. So the reason is that the frequency is the time taken divided by the number of oscillations. Rather, frequency is the yes, is the number of oscillations divided by the time taken, whereas period is the time taken divided by the number of oscillations. One interesting thing with simple harmonic motion is that there are a lot of formulas for us to derive. For example, using the fact that the length of an arc equals to the product of the radius and the angle in radians. So now we can safely say that the angular velocity is equal to the angle in radians divided by time. So that's the change in the angle with respect to time, and that is equals to the angle is equals to s over r. So when you have theta measured in radians, so you can remember that radians is actually the length is the angle subtended by a circle whose arc is equal to the length of the radius. So that is one way of understanding it. Now basically we can rearrange the formula to give equals to s over t multiplied by 1 over r. So when we evaluate this, when you exchange the denominators, we have the angular velocity equals to the product of the velocity and the inverse of the radius. That's v over r. When we cross multiply that, then v equals angular velocity times the radius or the amplitude. So hence the linear speed equals the product of the angular speed and the radius or amplitude of the simple harmonic motion. Now let's solve this example, which states that a spring makes 660 revolutions in 15 seconds. Find the period and frequency of the vibration. Now you recall that the period equals to the time taken divided by the number of vibrations. So basically in this case you have the time taken as 15 seconds and the number of vibrations as 60 revolutions. So when we plug in our values into the equation, we'll get 0.25 seconds as a period. Now next, from our previous knowledge that the period and the frequency are inversely related, then the frequency is the inverse of the period, that is 1 divided by 0.25. When we do that, that's 4 seconds, 4 per second, or 4 hertz. So I didn't mention this earlier, but the unit for frequency is known as hertz. Now let's talk about the acceleration of the body. Now you will recall that we said the projection of that point P on the x diameter is equals to x equals a cos theta, and then here we know that theta is equals to the product of the angular velocity and time. So let's plug that into our equation. So we have the x dt equals minus wa sine wt. The reason for this is that when you derive cosine, you get minus sine. So then when we do that, this dx dt is a rate of change of displacement with t, and that is equal to the linear velocity. So you can say that this is equal to minus wa sine wt. So this is the linear velocity of the object. So to obtain the acceleration, we differentiate with v with respect to t, and hence a equals dv dt. That's when we differentiate for the second time, we'll get minus w square a cos wt. So when we shorten that, that becomes minus w square x. So because x equals a cos wt, so the acceleration is equals to minus w square x. Now what we just done, we've looked for the linear acceleration. If we're looking for the angular acceleration, there was a different procedure for that. So but it's defined as the time rate of change of angular velocity, and it is expressed in radians per second per second. That is radians per second squared. Now if the angular velocity is changing from wo to wt in t seconds, then the angular acceleration is equals to wt minus w over t. And from this equation we have that we have that angular acceleration, or rather angular velocity, equals to the angular linear velocity divided by the time, rather divided by the radius. So that's v over r. When we cross multiply, we have v equals r times angular velocity, and then angular acceleration will be equals to the product of 1 over r times the angular. This is the ratio between the the linear velocity and the time. When we rearrange the equation, so we'll get that is the linear acceleration divided by the time, divided by the radius rather. So when we cross multiply, we have linear acceleration is equal to the product of the angular acceleration and the radius of the simple harmonic motion. Now, as I mentioned earlier, simple harmonic motion is full of relationships. So you can see that in this case, the square of the angular velocity is equals to the the quotient of the acceleration to gravity and the length of the string. So this string is a string that bears the mass that is oscillating in angle in simple harmonic motion. We won't talk about the derivation of this, but basically you can see that if you plug that into the equation, t equals 2 pi over angular velocity. That's, as you can see here, you can represent that as 2 pi over the square root of g over l. So that would be equals to 2 pi root l over g. So this is the equation that represents the relationship between the the um the period of motion and the length. So for a pendulum, there's a known fact in the pendulum and in simple harmonic motion that anytime you have an object oscillating held by a string and it's oscillating in simple harmonic motion, the period of motion is only determined by the length. So other factors will not affect it. Only the length of the string can change the period of motion. And this concept is very widely known in the oscillation of systems and is usually applied in when you want to alter the nature of systems. You can just alter the length because the length is directly proportional to the period. You can see that when you increase the length, you're going to increase the period. So the period of motion is only dependent on the length. So let's remember that. In simple harmonic motion of a pendulum, we also have energy because energy is the force that is the thing that is causing the motion. So because of this energy, we can say that they are divided into potential energy and kinetic energy. First of all, when we talk about the potential energy, it is due to the height. So a body getting in simple harmonic motion, we have more potential energy with the increase in the height. So as you can see, when the pendulum bob swings upwards, at that maximum position, at that highest point, it has the maximum potential energy. Then when it swings down to its lower equilibrium position, you can see that the kinetic energy is maximum and the potential energy becomes zero. When it swings back to the maximum high position, the potential energy returns to the maximum and the kinetic energy returns to zero. Now, if you study this motion very well, you can see that there are different reasons for this. For example, you know that the kinetic energy is dependent on the velocity, and when the object moves to the end, that is the maximum displacement from the equilibrium point, you can see that it momentarily stops. So that means the velocity momentarily becomes zero. As a result of this, the kinetic energy is zero. So you can see that there's a reason for every formula we derived in simple harmonic motion. Now, the motion of a body in simple harmonic motion is due to energy, right? Now, when we talk about this energy, it also involves work. So, work is done from when the pendulum swings from one stage to another. But as we all know, in the world, there's no way you can do work without friction. So, there's the work that kind of takes out of each of the energy. So as the object oscillates, it loses energy and it gets to a stage whereby by the amplitude that means the object becomes static, it no longer oscillates. Now that's the characteristics of damped oscillations. So as you can see in this second diagram, we have a damped oscillation. The oscillation of an object is just like a wave. So when the amplitude shortens and it shortens till it gets to zero, that's called a damped oscillation. But then there's another alternative. In an ideal environment, when there's no friction, when there's no opposition to the motion, you can say that we get a free oscillation. And these free oscillations, they don't occur in nature. They are actually just imaginary creations of the human mind. But you can also make an object oscillate freely by the um, by the by the phenomenon we call resonance. So if you begin to augment the amplitude for a fixed interval of time, you will notice that the object will keep rotating with that same amplitude and that frequency, and that is called resonance. So when you resonate that oscillation, you can be able to keep it in free oscillation. Now I have to agree that in this episode we've covered quite a lot. So because of that, we are going to run through a summary of all the concepts we've been talking about. So first of all, we talked about simple harmonic motion, which the acceleration is always directed towards a fixed point and is directly proportional to its displacement or distance from that point. Secondly, we also talk about the essential characteristics of an oscillatory motion, which are the fact that it's always regular and it's repeated. Third, we derive some formulas. For example, the acceleration is equal to the negative of the square of the linear of the angular velocity and the product of that with the amplitude. So the period is also given as the ratio between 2 pi and the angular velocity. We have the frequency is the inverse of the period. By also when you overturn the period, you get the frequency. Then we also have the linear velocity is equal to the product of the angular velocity and the amplitude of motion. So finally, we also said the angular velocity is equals to the ratio of the angle displaced and the time taken for that displacement to occur. So these were all derivations, and finally we derived the formula for the period of a simple pendulum by substituting the value of the angular velocity, and so we get that as 2 pi root L over G. So this is a very common formula, and it's very useful in understanding the states and properties of systems like this. So now to round this video off, we'll be dealing with a question that will help you to understand this concept. So this is a question on the screen. You can also try it, but I'll also offer the solution in a separate episode of this series. So I hope you understand this concept of simple harmonic motion, and hopefully I'll see you next episode. Thank you for watching.